Hello everyone, my name is Pandya Khushi. Currently I am studying at Marwadi University in ICT department, and now I am going to tell you about tell you something about arithmetic operations of op-amp. First let us see about the pin diagram of 741 op-amp. Here you can see in a picture there is a total 8 pin. First and fifth pin is for offset null. Second is for inverting input voltage. Third is for non-inverting input voltage. Fourth is for negative supply. And seventh is for positive supply. And sixth number pin is for output voltage. First let us see about inverting amplifier. Inverting amplifier is used to get output voltage in amplified and differentiated form of input voltage. As you can see in a circuit diagram, we have connected supply voltage with the inverting input voltage, and we have grounded non-inverting terminal. So let's see this circuit in a multisim. So we have connected output with a CRO so that we can get a appropriate graph of the input and output voltage. Let's play. Here red color is for input supply voltage and blue is for output voltage. In a positive half cycle we get negative output, and in a negative half cycle of input we get positive amplified and differentiated output. After that, non-inverting amplifier. The circuit is the same as inverting amplifier, but here we have connected the supply voltage is with a non-inverting terminal, and we have grounded inverting terminal. And we have connected output with CRO so that we can see the comparison between output voltage and input voltage. Let's see the circuit in a multisim. So we have connected supply voltage with non-inverting and inverting terminal grounded. So just play. See, red color half cycle is for input voltage and blue is for output. Positive half cycle, positive amplified waveform, and negative half cycle, negative amplified waveform. This is the circuit of non-inverting amplifier. After that, summing amplifier. In summing amplifier circuit, we have used n number of input resistor and supply voltage. It is connected with inverting terminal voltage. By theoretical analysis, we got the output voltage formula like this: minus Rf upon R1 into V1 plus Rf upon R2 into V2 plus Rf upon R3 into V3. Here R4 resistor is denoted as feedback resistor, and we have connected output voltage with a CRO so that we can see the waveform of it. In this circuit we can also use a multisim because we get the DC output voltage in summing amplifier. So let's see in a multisim. This is the circuit. We have used 3 resistor of same value, and feedback resistor is also have same value, and input supply voltage is for 1 volt, 1 volt and 1 volt. By theoretical analysis we should get minus 3 volt total from the formula. So let's check. Here you can see in a channel B we got minus 2.99 voltage is approximately 3 volt, and we can also see this using multimeter. Minus 2.99 voltage, approximately 3 voltage. This circuit is called summing amplifier. After that, average amplifier. Average amplifier is a modified form of a summing amplifier. In this circuit, if we consider all input resistance have same value and our feedback resistance is equal to 1/3 of all input resistance. Here you can see in a circuit diagram all input resistance have the same value and feedback resistance is having 1/3 of the all input resistance. So that output voltage of average amplifier is equal to minus of V1 plus V2 plus V3 divided by 3. Here we have used 3 resistors, so divided by 3. If we used 4 or 5 resistor, then according to that we have to write that value. Let's simulate in a multisim. Supply voltage is 2 volt, 2 volt and 2 volt. So by theory we should get minus 2 volt, because 2 plus 2 plus 2 is 6 and 6 divided by 3 is 2 volt. So here we can see that channel B is seeing minus 1.99 voltage, which is approximately 2 voltage. Same as previous, we can also check this about with the multimeter also. After that, subtraction amplifier. In a previous all amplifiers, we have connected only one terminal with a supply voltage and other terminal with ground. But in this circuit, we have connected both terminal with a supply voltage. So the output of this circuit is proportional to the difference of non-inverting input minus inverting input. As you can see in a formula that R3 upon R1 into V2 minus V1. But in this circuit, I have considered value of all resistor is the same, so that R3 upon R1 equal to 1 and V output is equal to V2 minus V1. Let's simulate in a multisim. We have given 6 voltage to non-inverting terminal and 2 voltage to inverting terminal. So by formula we can say that 6 minus 2 equal to 4 voltage. So output should be approximately 4 voltage. 4.002 voltage. This is the circuit of subtraction amplifier. After that, multiplication amplifier. This circuit is similar as a inverting amplifier. we have put one input resistor and one feedback resistor so that we can get output according to that. When we have multiplication amplifier, the value of input resistor or R1 should be 1, and we can consider value of feedback resistor or R2 anything, because our formula is V output equal to minus of R2 or feedback resistor into input voltage. So let's see in a multisim. Value of R1 is equal to 1 and value of R2 is 2k. So by formula we should get 2 into 2 approximately 4 voltage, minus 4 voltage. So here you can see in a channel A minus 3.99 voltage, which is approximately equal to 4. We can also use multimeter in place of CRO to get appropriate output. After that, division amplifier. Circuit is similar to previous one. We should only change the value of resistance. In this circuit, we should consider feedback resistor is equal to 1 or R2 equal to 1 and R1 is as any number. So that output voltage is equal to minus of 1 upon R1 into input voltage. Let's see in a multisim. For division amplifier, the value of R2 or feedback resistor should be equal to 1. According to formula, we should get minus 1 voltage. Let's see. Minus of 0.99 voltage, which is approximately equal to 1 voltage. After that, integrator amplifier. In this circuit, we have replaced our feedback resistance with a capacitor. So we have connected a capacitor, so its resistance is equal to XC, and value of and by theory we got our output voltage is equal to minus of 1 upon R into C and integration of input voltage with respect to time. We have given our supply voltage by function generator so that we can get a control on a frequency, because by changing the frequency we can see that our output voltage is changed. Let's see in a multisim. Here we have connected our capacitor in place of feedback resistor, and we have given 2 voltage peak and frequency is 30 Hertz. So let's check. In output we should get amplified and integrated waveform. Here you can see the red is for input and the blue is for output. Red is in a square wave and while blue is in a destroyed sine wave. Means not triangle and not a sine wave, but it is in an integrated form. Let's check by changing frequency. I have decreased frequency so that the blue waveform should be similar to the square waveform or a triangle waveform. Let's see. It's similar to the square waveform, and it is also in amplified form. After that, differentiator amplifier. In this circuit, we have replaced our input resistance with a capacitor, and so that our output voltage is equal to minus of R into C dV by dt, or differentiation of input voltage with respect to time. In this circuit, we can get output in terms of spike. Spike means when our input voltage changes its cycle from positive to negative or negative to positive, we get our output voltage. Let's see in a multisim. In this circuit, I have given input voltage of 2 and our frequency is equal to 1 Hz. Let's check. Here you can see red is for our input and blue is our output. While input voltage is changing its cycle, we get some output voltage. Thank you for watching this video.